Okay, we're going to look for interaction in a multiple regression model. The fun never stops. Okay, we're going to try to make a prediction model on which of the IVs or which combination of the IVs works best for the weight loss. Okay, so the criterion is weight loss and the IVs are above. So let's go ahead and start looking at the questions. Question 1, what are the predictors? That's pretty basic. I tell you right up at the top. Okay. The predictors are the number of hours exercise per week, calorie reduction per week, and the last one is the number of hours a person sits in front of a computer all day. So those are our IVs. And the criterion, right, that's our DV, that is the amount of weight loss in pounds. So again, we're going to recap. We're going to take these 3 IVs and try to develop a model that will predict the DV. And then with this video, we're going to show you how to check for interaction between the IVs. Number 3, is the sample size large enough? Yes, we have our sample size, I believe, is 154, which is bigger than 50. Okay, so a minimum size to run a multiple regression model that's going to ensure a power of at least 0.80 should be a minimum of 50, and we got about 3 times that, so we're good to go. So let's move to the next one. Which of the assumptions were violated? Okay, now it's time to do some work. So let's go ahead and pull up our data and open up SPSS. Please give me 1 second. All right, here is the data in an Excel spreadsheet. What we're going to do is go ahead and cut and paste that right into the SPSS. So just highlight all the numbers. Do not highlight the letters, just the numbers. Hold on a second. I'm going to hit Control C. I'm going to open up a blank SPSS. I'm going to click it in the upper right hand corner. Make sure that I am in data view, right? Make sure we're in data view down here. Go to the column 1, row 1 spot, right click, paste, give it a second. Okay, there's the data. We're going to rename the variables now. So the first variable was?
Daily. No, per week.
Hours of exercise. Number 2 was? Calorie reduction. Number 3 was? Sitting in a computer. Just sitting in front of a computer. So we'll just put sitting computer. And the DV was weight loss, right? Oops, no spaces. Okay. And in this multiple regression, all the variables are scale, 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 scale. And I believe we're ready to go. Okay. All right, the Copilot insists that we're going to change the name to from the third variable from sitting to a computer to sitting minutes, because that's what we're actually counting. So I apologize that the Copilot is kind of pushy. Assumption number 1 for multiple regression. Multivariate normality. It's always the same. Is the data normal? So we're going to use a Mulholland-Obis distance test. So let's get going. Go to Analyze, Regression, Linear. So remember, this is just the Mulholland-Obis test, so we're going to put the DV in and the IVs in. Click OK. We're only going to look for nothing here. Let's unclick these boxes. Okay. I think the Mulholland-Obis is under the Save button, and there it is. That's the only one we're checking for here, okay? That's going to tell us if we have any outliers or not. Click OK. And what we're going to find is our maximum Mulholland-Obis number. So there's our maximum distance. So it looks like it's about 16.9. 16.9. So now we have to open up our critical Mulholland-Obis worksheet. It's an Excel. Hold on. And here it is. Okay, this should be on the Moodle somewhere. So our alpha is always 0.05. Our N is, I believe, 154. And our K is the number of IVs, and we got 3. And let's take a look. All right, so good. Our critical Mahalanobis distance is 18.5. So we did not go over that. Let me pull this up real quick to double check. Right? We did not go over 18.5. So therefore, we do not have any residuals that need to be removed. Okay, so we're just going to keep on pressing on. Assumption, which is the Durbin-Watson test for autocorrelation. So let's go ahead and do this one. Please hold.
Look at your smile. Give you the look.
All right, Copilot's giving me a dirty look. So let's check for autocorrelation. We're going to go to Analyze. Regression. Linear. And it should be pretty set before. Right? Everything's where it needs to be. But again, we're just looking for the Durbin-Watson, and I believe it's right here. Unclick these other ones until we're ready. Okay, again, we're just going to check the autocorrelation looking at the Durbin-Watson test statistic. Click OK. We want the Durbin-Watson to be between 1.5 and 2.5. So keep your fingers crossed. There it is right there. So it is within the OK range. Therefore, the autocorrelation assumption was not violated. Yay us.
Crazy over you.
Right? So autocorrelation was not violated. Okay, moving on. The assumption of linearity. What we're going to do is make a scatter plot between each IV and the DV. If the R squared is 0, that means we will have violated the assumption of linearity. So let's just pull them up and do them real quick. So we're going to go to Graphs, Legacy, Scatter. Pull it over here. We're doing a simple. We're going to define it. So the DV is weight loss. And the first IV, we're going to do hours of exercise. And we can only do them one at a time in SPSS. Let's click OK. Here's the graph. We're going kind of fast because we've done this in several of the other previous videos. So if you need some more help, please check out some of the other videos. But now we're going to add a trend line. We're going to double click. Best fit line, my bad. Linear. Okay, so again, if this R squared is 0, we're in trouble, but we can already tell it's not. Okay, it's pretty close to 0, but it's not 0. So IV number 1, we did not violate the assumption of linearity. So let's go to IV number 2. Same thing. Graph, legacy, scatter. We're going to do the simple. We're going to define it. We're going to kick out the hours, put in sitting minutes as the IV, click OK, get a new graph. Hold on a second. Got a new graph. Okay, so the DV is always the y-axis here. Double click again, add a best fit line, it's preset, click OK. Now this R squared is nowhere close to 0, so we did not violate the assumption of linearity here either. So let's do the last one real quick. We're going to go to Graphs, Legacy, Scatter. Same thing, simple, define. Out with this IV, in with the calorie reduction. That's the last one. And we get our new graph up here. Double click, add best fit line, linear, close. Again, this is not 0. It's close to 0, but it's not. But again, none of the assumptions of linearity were violated for any of the 3 IVs. So let's move on. Again, here are the correlation plots. I'm sorry, what the hell are they?
Scatter plot.
Got it. All right, so for the next assumption, we're going to check the homoscedasticity, which we're going to do a Z-pred versus a Z-residual graph. So hold on one second. Analyze, regression, linear. We're going to plots, right? We're checking for the homoscedasticity. And your y is always your residuals, and your predicteds are always your x, and we don't need a histogram, so just click OK. Click OK again. All right, you just double click. You're going to add your best fit line. It should be the preset. You're going to close it. Okay, now we're going to add the lowest line. Let me pull it down in here. You're going to double click it again. We're going to check the lowest line. That's going to tell us if our data is homoscedastic or not. You click the add best fit line again, and the preset should be the lowest line. And there's our lowest line. So it looks to me like we may have minorly violated the assumption of the homoscedasticity of data, but I don't really think so, because most of it is a relatively horizontal flat line until you get to like the 3/4 point over there. So I'm going to say we did not violate the assumption of homoscedasticity of variance. What are you, a steam pot or something? What are you, a steam pot or something? All right, last assumption, multicollinearity. Let's go ahead and take a look. Let's pull up our data. We're going to go to Analyze, Regression, Linear, get in there. Weight loss is our DV. The other three are our IVs. And again, we're just checking for multicollinearity. So we're just going to unclick everything and click the collinearity diagnostic box. Continue. Okay. And here's our multicollinearity test statistic. So tolerance. If tolerance was less than 0.1, you would have violated. If the BIF was greater than 10, you would have violated. So according to our data, we did not violate multicollinearity. Okay, let's get back to the good stuff. That was my co-pilot. All right, we're just going to go ahead and run the regression model regardless of interaction. That's going to come here next, but let's go ahead and just run the regression model. Going to go to Analyze, Regression, Linear, and everything should be where it is. Okay. So I'm just going to run it with estimates and the model fit and R-squared and descriptives and all right, change. We don't need R-squared because it's a simultaneous, right? So we're not changing models. So again, and then the Durbin-Watson, we're just going to click Continue and click Run. So this, again, this is just a regular simultaneous multiple regression model. So let's look at it real quick and see what this means. All right, the first box is descriptives. The mean standard deviation is not that big of a deal. The second box, correlations. So here's your DV, and here's the correlations. Here's the significance of them. The only one that has a significant correlation to the DV seems to be sitting minutes, okay? So now we're going to look at the R-squared. That's a very important. Well, according to the output, it looks like the R-squared is 0.245, and that tells us with this model about 24.5% of the variance of the DV can be explained. The ANOVA is significant, so that means that this is a significant regression model. Now we're going to look at the beta weights, okay? So this is each IV's significant contribution to the outcome variable. All right, hours of exercise, not significant. Calorie reduction, not significant. Sitting, again, according to this plain Jane model, sitting is the only IV that is significantly contributing to weight loss. Yeah. The co-pilot and I were just discussing, we're very thankful that this isn't a taped thing and everything's digital, so we're not wasting a lot of money because she certainly goofs off way too much for my taste. Okay, so the SPSS output. It says that, yes, we have a significant regression model. What that really is testing is, it's testing against a regression of 0. That would be the null hypothesis, would state that the regression model is a 0 regression model, and this says no, that is not accurate. So we do have a significant regression model, and the SPSS also answered our question 6. Which of the predictors were significant? The only one was the sitting minutes, okay? Right, there's your significance level. Where is it? Right there. Boom. Boom, 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 boom. And it's got a pretty big beta coefficient. Okay, so it looks like, according to this basic model, the more you sit, the less weight you lose. Okay, so it's a negative correlation. So let's move on. The effect size of this is, let's pull up our SPSS. And there's the dreaded R square. So in this problem, it's about 24.5% of the variance of the DV, weight loss, can be explained by this model. And according to Cohen, this is somewhere between a moderate and strong regression. Okay, even though we have a significant regression model, we have not addressed the interaction, right? There could be interaction between the hours of exercise, calorie reduction, and the number of sitting minutes, okay? So that's what we're going to do next. We're going to check for interaction. So please stay tuned. All right, now we're going to run the interaction model. So in other words, we're going to rerun this entire regression model, but we're going to add in any interaction effects that might come about. So please hold. This is when we will center the continuous variable. Centering. We center to check for interaction between continuous variables in a multiple regression model. That is a very important verb in multiple regression, centering. All right, I'm going to briefly explain what centering is. First of all, it's only found in multiple regression. It might be used later, but it's only used in multiple regression models. And only the continuous IV, or the predictor, it has to be continuous, not categorical. We will be doing something later about that. But it has to be a continuous IV in a multiple regression model. And so this is how you center an IV. So you take a continuous IV, you find the mean of that IV, and you subtract it from each raw score from the original IV. So that the new centered variable, the new centered value, is going to be the individual minus the IV mean. And that new term is going to be called the centered term. So you're going to do that with every piece of data. We're going to go ahead and show you how to do that in SPSS right now. Please hold. You should be able to use information that you already have in the SPSS output, but I forgot to write down the means, so I'm going to go ahead and get the means of our IVs, descriptives, frequencies, just the IVs. Oop, get out of there, you. And just the mean. We're going to use those to center our variables. So here's the mean. Hours, it's 10.9. Calories reduced, 3145. Minutes sitting, 185.3. Okay. So this is how you create a centered variable. You go to transform, compute variable. First one, I'm just going to name them all center. First one I'm going to do is the hours. So I'm going to put hours into the box. I'm going to hit subtract. And the mean for hours was 10.9. Click OK. Do it again. Transform, compute. I'm going to hit reset. Clear it out. The second one is going to be center calories. I'm going to put my calorie reduction in there, subtract, and the mean for calories was 3145. Click OK. Transform, compute, reset. Last one is center sitting minutes, just sitting. And sitting over into the box, subtracting the mean of 185.3. Okay. So we've created 3 new variables. Let's take a look at them. Okay. So there's your centered variables. Another reason we use centering is because we're about to check for interaction. We're going to multiply the variables together, but the units are going to cause chaos. So That's why we center the data. Another reason we use centering over like standard deviation, if you remember, most of your data, practically 100% of your data should fall within -3 and +3 standard deviations of the mean, and that's just not a big enough spread. So centering allows us to have a much larger spread, and therefore the data from it will be much more accurate. Okay, so we figured out what the centering stuff is. Now we're going to go ahead and create our interaction terms. We're going to go to transform, compute variable. Let's get this over here. We're going to reset it again, clean it out. So the first one is going to be hours and calories. Right? We're naming it here. This is our naming box. So we're going to put center hours and then hit the asterisk, that's multiply, and then center calories. Okay? Boom. Next one, transform, compute. Clear this out. The next one is going to be the interaction term between hours and sitting. Again, this is our naming box. So let's put in hours centered, asterisk, sitting centered. Done. The third one is going to be compute variable, and it's going to be calories sitting. Calories sitting. And let's just get this one out. So let's find our center calories. So where is our center calories? Put that in. And click OK. And our last one is going to be all three, right? So we have calories, we have sitting. So let's do our star and put our center hours in there. And just call it calories, sitting, hours. And I'm getting a lot of, do you want to overwrite stuff? I've been playing around with this for a while, so this I'm just fixing the data. Please pay no attention to these existing variable things, okay? But we should have everything fixed. So let's look at the data. So this is your hours calories interaction, hours sitting interaction, calorie sitting interaction, and then all three together. So we're good to go. So we're going to go ahead and run our multiple regression model with our interaction man-made variables. So please hold. Analyze. Regression, linear. All right, so here we go. We're going to go put in the weight loss as the DV. So what we're going to put in the independent variables are the centering variables first. Okay, 1, 2, 3. So those are our centered variables. We're going to hit next. We're going to stick in our first interaction check, right? Hours and calories. Click it into the box. Next. We're going to hit our second one, hours and sitting. Click it into the box. Next. The next one is calories and sitting. Next. Last one is all three, calories, sitting, and hours. Don't hit next anymore. Now we're going to go into the statistics, and we want to see if there's an R squared. We can click these two, the partial and the collinearity, even though we already know what's going on with the collinearity. We're already good. And Durbin-Watson, we really don't need that. We already know, so let's click continue. And I believe that's the only thing we need. Let's click OK. Okay, you're going to scroll down to the model summary box right there. So, okay. So the first model, that is with the centered the centered variables only. You'll notice that the R square is the same as the original predictors. And it should be because the variance did not change even though we centered it, okay? So the second model is with the first interaction term between hours and calorie. You go all the way over here to the significant F change, and it wasn't a significant F change, okay? So that means there was no interaction between hours and calorie. The third model was with the interaction term of hours and sitting. You go all the way over here to significance change. It almost made it, but not quite, okay? So that means there is no significant interaction between hours and sitting. Close, but no cigar. Number 4, bang, that's your money right here. Because the significance here is less than 0.05, that means that, yes, you do have a significant interaction with whatever the interaction term was for number 4, and that was the interaction between calories and sitting. Okay, so you do have serious interaction between calories and sitting. This last number 5, that was with all 3 of the variables mixed in one giant interaction. And according to this, there was no interaction between the 3 variables. Shh. Will you be quiet over there? It was close. All right, here's question number 9. Identify all significant interactions. I think we just did that with number 8, accidentally, of course. But the only significant interaction between the predictors was our 4th model, and that was the one that had the 3 centered variables and the interaction term between calories and sitting. So calories and sitting, definite significant interaction. And if you look at number 3, right, this is relatively close to 0.05. So it's a little bit borderline between the interaction between hours and sitting. All right, what is the change in R squared, or the effect size for the interaction effects, and what does it mean? Okay, so since we only had one interaction effect, what that means is the R squared change from the original of 0.245, it adds on an additional 0.052, so there's your new R squared. But again, that's only good for the interaction model. So what that means is when you added that interaction effect between calories and sitting, you made the model a little bit more stronger, right? You added about 5% more explained variance to your R squared. So you went from a moderate to strong model to now you have a strong model, right? Anything over 0.26 is considered strong by Cohen. So nice job. No giggling allowed. But we answered this question already as well, okay? So what this means is that the new R squared with the interaction term between, what was it, calories and sitting, there's your new R squared, 3.14. And that is considered a strong effect size based on Cohen's table. Okay, now they want the beta weights of the significant interactions, of which we only had one. So let's go back to our SPSS. And we're going to scroll down to the coefficients table. There it is. And because this is the model 4, right, that was with the 3 centered variables and the interaction term that was significant. And we're going to look at the column which is the beta weights. There's the beta weights. So let's go down to number 4. And calories and sitting, that's what we're looking for. Oops, don't click that. There it is right there, 0.234. So that's the beta weight. Since sitting in front of a computer was the only significant predictor, the only possible moderator could be calorie reduction variable, because if we look at the 4th model, again, that's the only one that had the significant interaction, and that was between calories and sitting in front of a computer. Okay, so the only possible moderator was probably calorie reduction. All right, we're going to write out the final regression equation using the unstandardized B weights. All right, now we got to go back to SPSS. We're going to regenerate some unstandardized B weights with what we now know. We're going to go back to the original predictors. We're going to use hours of exercise, calorie reduction, and a number of minutes sitting, just the plain predictors, no centering or anything. But we do have to make a new interaction variable, right, between calories and sitting. So we're going to go to transform, compute, and we're just going to call this calories sitting 2 or O2 or something. We're not going to confuse that with the original one. And we're going to take the calorie reduction, bump it in there, hit our asterisk, sitting, minutes sitting, done. Now these aren't centered, right? So we're just doing this to get the beta weight so we can write out the prediction equation. So let's see what we got here. I'm just checking the actual data, make sure it did show up. Okay, there is our new variable. Okay, wow, big numbers. Okay, here we go. So we're going to generate new unstandardized beta weights. We're going to go to Analyze, regression, linear. All right, we're going to reset this mess. We're going to stick hours, calories, and minutes independent. Weight loss is dependent. And here's our new interaction term. That goes in there as well. Remember, we're just looking at the unstandardized B weights, and there they are right there. So these are the ones that we're going to use in our prediction model. So hold on. So here's the final prediction equation. Okay, that's a predicted Y up there. But this X1 is the hours of exercise. X2 is the calories reduction. X3 is the minutes sitting in front of a computer. And this X2, X3, that's the interaction term between calories and sitting. Even though this coefficient is very, very tiny, what is that, 1/100,000th? You got to remember that with the interaction term that we made, we multiplied the minutes sitting times their calorie reduction unit. So those numbers were huge. If you remember, they were in like the 20 or 30,000s. So this kind of makes a lot of sense. And this number right here, this is your constant term. So there's your final prediction equation, your final prediction model. And it's not bad, right? It had what, 36%? I'm sorry, 31.4% accuracy rate. So that's pretty strong. Here comes the fun part. We're going to write up the results of this multiple regression using APA formatting. So please hold. And finally, here is the APA format of the write-up of a multiple regression with interaction. I'm not going to read it here. It's best to just go pull this from the answer page, but I will scroll down slowly. Scrolling, scrolling. And that's it for question number 15. And that's all she wrote. Hope you enjoyed it. MGZ and Copilot out.